Hello everyone, my name is Toanir. I'm a PhD student at Téléconsult Paris, and today I'll be presenting our paper on leaderless state machine replication. So let's start by giving some context and principles necessary to understand this presentation. So nowadays we have modern internet services maintain more than one copy of an object. And each copy is all located on a separate server, or as we call them, replicas. This is illustrated on the right by P1, P2, and P3. Clients, they interact with these replicas by sending commands and share logically these objects. So it begs the question, why to replicate data? One of the reasons is for performance. Consider the example where a client connected to the replica in South America wants to send commands to the replica in North America, replica P2, but the geographical distance is too big. So what we could do by replicating data is put in a closer replica to it, and then it can communicate easier. The geographical distance is smaller. Another important reason is reliability. We can mask replica and network failures. So let's suppose the same scenario where a client in P1 is sending commands to a replica P4. This replica fails, it can be relayed to the replica North America or replica P2. So now that we have understood why replicating data is important, comes the question of how to do it. We use a technique called state machine replication, or SMR. It is very important to notice that since we have multiple clients accessing and possibly modifying the shared object, it is necessary to have some kind of consistency across the replicas. For this paper, we consider the strongest one, strong consistency. So on the right, on the figure on the right, we can see that the arrow explicits this connection. It's the ordering between the commands. So in classic SMR, a classic algorithm, Paxos, we execute commands in the same order. In generic SMR, we execute non-commuting commands in the same order. So we can see that on the right, what we have is a partially ordered log. And this paper is focused on leaderless SMR. So what is the difference between leaderless SMR and the previous SMR techniques? So the very first important difference between leaderless SMR and the other techniques is that in leaderless SMR, we relies on the notion of a dependency graph instead of a partially ordered log as found in generic SMR. A dependency graph is a directed graph that records the constraints defining how commands are executed. Note that there is a cycle between A and C. On the case of generic SMR, this wouldn't be possible. The partially ordered log is represented as a DAG, a directed acyclic graph. It's important to understand this terminology that for some command C, the incoming neighbors of C in the dependency graph are its dependencies. In leaderless SMR, a process holds two mappings, depth and phase. The mapping depth is a dependency graph storing a relation from the set of commands to the power set of commands union two special symbols, bottom and top. Initially, for every command C, the dependencies of that command is set to bottom. This corresponds to the pending phase. When a process decides a command C, it changes the mapping depth C to a non-bottom value. This is done through the operation commit, which assigns D taken in the power set of commands to depth C. So consider, for example, that the event commit was done. So we have that C has its dependencies A and B. So we'll have that an arrow from A to C and an arrow from B to C, and there is no longer, and C is no longer pending. Now we have the same for A. A is committed with its dependencies, the set containing only C. So it has there is no longer an arrow from bottom to A, and we have an arrow from C to A, yielding this dependency graph. So let depth stars of C be the transitive closure of the depth relation starting from a command C. A command C is considered stable once it's committed, and no commands in depth stars of C is pending. Here we can see that only C is stable because all the other commands are still pending, since their depth star actually include command D, which by the way is pending since it has bottom as its dependency. In this example, all commands are stable. A command C gets aborted when the dependencies of C is set to top. So you can see here it's set to top. And in that case, the command is removed from any dependencies of other commands, and it will not appear later on. So now that we have understood the main concepts of the abstraction, we move on to present the guarantees that leaderless SMR give us. So we have stability, that for each comment C, there exists a set big D, such that if C is stable, then depth of C is set to that set big D. And consistency, if A and B, if comments A and B are both committed and conflicting, then A belongs to the depth of B, or B belongs to the depth of A. So this encapsulates some of the concepts that have been shown to you here. Now, to solidify the concepts, I'm going to provide an example. We have two replicas P1 and P2. P1 submits command A, and replica P2 submits commands C, D, and B. It's important to notice that A and B do not commute, and B does not commute with D and C. We have the first commit at some point in replica P1 using dependency graph G1. We can see that B is still pending because there is an error from bottom to B. And then we have the commit of C, and the replicas decide that the dependency is empty. So yielding dependency graph G2, we can see that there is no longer an error from bottom to C. Then we have the commit of B with the dependency set C, D, and A in G3. And now an interesting case, we have the commit of two different commands that will yield the same dependency graph. We can see in G4 that only C is stable. And then we have the commit of D with an empty set yielding graph G5. By this point, you must be asking yourself, how do we execute commands using this abstraction? So I'm going to explain this now. A command gets executed once it is stable. I'm using the same example, the same graph G5 from the example before. And we can see that all commands in G5 are stable. Therefore, they can be executed. How do we deal then with the case where A and B depend on each other? So we break cycles deterministically based on the identifiers of the commands. So I'll provide an example. Consider that there was this set of commits. So we have C and D. This could have, we have the commit of C, the commit of D, the commit of A, and the commit of B. For the execution, we would have that a possible execution would be execute C and D. This could have happened in any order. It could have been execute D and C since they commute. So an order there is not enforced. And then we have execute of A and then execute of B if the A is smaller than B. And another possible scenario would be that we have execute of C, D, B, and A if B is smaller than A. With these concepts in mind, we ask ourselves the question, what is the essence of leaderless SMR? And now we are ready to answer it. So we understood that leaderless SMR does not compute an ordering over conflicting commands. Conflicting commands must simply observe one another. That was encapsulated in the consistency property. So how do we capture this feature? We propose a decomposition into two services, the dependency discovery service and the consensus service. One can see that algorithm 2 depicts the abstract protocol to decide a command. The coordinator of C is the initial process in charge of submitting the command to the replicated state machine. And in lines 5 and 9, we can see that the algorithm computes a set of dependencies of a command abiding to the properties stated previously, stability and consistency. It uses a dependency discovery service in line 3, the DDS, and a family of consensus objects that it is instantiated for each command in the set of commands. We can see this in line 4. And a failure detector D that returns a set of suspected processes. To create a valid proposal for the consensus service, a process P relies on the DDS service. This shared object offers a single operation announce that returns a pair D and B and a flag. When the return value is in the power set of commands, the service suggests to commit the command. Otherwise, the command should be aborted. When the flag is set, the service indicates that a spontaneous agreement occurs. That is a very important concept to grasp. In such case, the process P can directly commit C with the return of the DDS service and bypass cons. We can see that at line 4, cons is not highlighted. This is what we call the fast path. If the flag is false and it needs to go through the consensus service, we call it a slow path. As usual, let's strengthen our understanding of what I've just said with an example. So we have here a run of algorithm 2, where we have two replicas P1 and P2. They both submit non-commuting comments A and B. And at some point, we have that, after that, we have that G1 is pending. We have that there's an error from bottom to A. And we have the same in at some point in process P2 after submit of B. We have dependency graph G2. We can see that is also pending. And now there is a call to the DDS service. It announces command A, and process 2 announces command B. In this case, we consider that in replica 1, it returns the flag is set to true, so the fast path was taken. And in the second case, for replica P2, we have that there was the fast path was not taken. We took the slow path, so cons must be called to resolve, and we must reach agreement on the dependencies of B. At G3, there was the commit already, so we can see that we only have A in the dependency graph G3, and now we have the call to the consensus service in process in replica P2 to agree on the dependencies of command B. This happens, and we can see that B see A as its dependency, but A is still pending. It still has bottom as a dependency. So we have the send of both dependency sets for the processes, and at G5 they will reach the same dependency graph where A and B are committed, and B has A as a dependency. One can see that multiple implementations of the dependency discovery service and consensus service are possible. We have cast different leaderless SMR protocols into our framework, and I refer the viewers for the extended version of our paper, where this is further explained, because I will not have time to explain this in this presentation. And so we have the question, how to further characterize the protocols to get the differences between them. We propose a set of core properties: reliability, optimal latency, and load balance. The first property is reliability, a very natural property to have, as it captures the fault tolerance property of SMR. Note that parameter F captures the largest number of failures tolerated by the protocol. That means that we may not guarantee progress after F failures occur. Optimal latency is related to how fast the decision can be taken in some of these protocols. So consider a nice run. Every call to announce returns after 2 message delays if no conflicting commands exist. And load balancing, which is related to the concept of scalability. During a nice run, any n minus big F replicas can be used to announce a command. For example, Mencius use all the processes. So this kind of possibility needed to be expressed, and we express it in load balancing. Now, knowing all the properties we've proposed, I'll present another contribution from our paper, which is a complexity result. It's called the role theorem, that says that consider an SMR protocol that satisfies the role properties, then it is true that 2 times big F plus F minus 1 is smaller or equal to n. The inequation presented in the theorem expresses the trade-off between scalability and fault tolerance. And it's an interesting theorem because it differs a bit from the Lamport's lower bound, the fast learning theorem, in the sense that our theorem can capture and describe more accurately this trade-off in leaderless protocols. For example, the fast learning theorem doesn't explain properly Ipaxos, one of the most famous leaderless SMR protocols. So now I proceed to give the proof sketch for the role theorem. The proof goes by contradiction, using a round-based reasoning, and relies heavily on indistinguishability arguments. Let's assume the existence of a protocol P, satisfying to all the role properties and abiding to the inequation in the screen. And further, let us pick 2 non-commuting commands, A and B, belonging to the command set. The first step consists into partitioning our system into 3 sets of processes: big P1 and big P2, which are 2 disjoint sets of processes, each one with size big F minus 1, and the rest of the processes form big Q. It's important to notice that by cap, we have that there exists at least two distinct processes, P1 and P2, that belong to Q, and Q1 and Q2 are defined as we can see in the picture. So now, let us define a run lambda1 where no failure occurs, which starts with the submission of command A by process P1, and only the processes in big Q1 take steps. We know that this run exists by load balancing, since the size of big Q1 is n minus big F. And by optimal latency property of the protocol P, we know that by the end of round 2, we have the dependency set of A is set to the empty set. With an analogous argument, we can define a run lambda2 where only the processes in big Q2 take steps, and the dependencies of B are set to empty by the end of round 2. Now let us define a run lambda3 in which the processes P1 and P2 submit concurrently the commands A and B. By the end of the first round, the processes in big P1 will have received the same messages as they have received in run lambda1. The same will happen for the processes in big P2. They will receive the same messages as they have received in run lambda2. At the beginning of the second round, big P1 and big P2 reply to processes P1 and P2 the same way that they have done in runs lambda1 and lambda2 respectively. We consider that all the other messages sent in rounds 1 and 2 are arbitrarily slow. Now consider that the processes in Q crash at the end of the second round. By reliability, we know that commands A and B are stable in run lambda3. So let K be the first round in which the dependencies to A and B are different than bottom at a process in the union between big P1 and big P2. Now we build a run lambda4, very similar to run lambda3. The failure detector history is the same and the failure pattern as well. It starts with the submission of commands A and B in round 1 by process P1 and P2. And we have that the processes in big P1 receive the same messages as they have received in run lambda1, while the processes in big P2 receive the same messages as they have received in run lambda3. We consider that all the other message exchange between rounds 1 and 2 are considered arbitrarily slow. We can observe then that the following is true. For process P1, lambda4 is indistinguishable to run lambda1 up to round 2. So it must take the same decision by the end of round 2, which is a dependence of A, it's an empty set. And for a process P in the union between big P1 and big P2, lambda4 is indistinguishable to lambda3 up to round K. This implies that for both A and B are stable at this process P when round K is reached. So by the stability property, we have that for the processes P and P1, they decide the same dependencies for command A. The dependencies of A is an empty set. A symmetric argument to the one I just explained can be made using the previously mentioned run lambda2 and a new run lambda5 similar to run lambda4. And in this argument, we have that a process P in lambda3 decides that dependence of B is an empty set. So in the end, we have that in lambda3, both the dependencies of A and B are being set to empty, which is where we reach our contradiction, since this is harming the consistency property of leaderless SMR. The commands are non-commuting, so they should observe each other. So now let me refer back to the role theorem so that I can explain the concept of role optimality that plays a big role in one of our contributions of our paper. A protocol is said to be role optimal when the parameters big F and F cannot be improved anymore according to the theorem. For example, for n equal 5, there is a single tuple, big F and F, which is 2 and 2. And with n equals 7, there are two possible tuples, 2 and 3, and 3 and 2. For example, ePaxos is optimal for n equal 5, but we don't know of, for example, we don't know of any optimal protocol when n is equal to 7. To wrap up this presentation, I would like to do a small recap of the main contributions that can be found in our paper. The first and one of the most interesting ones is the decomposition into dependency discovery service and consensus service. And this is one that we are using more in depth in a continuation of our paper that is aimed at the Byzantine realm. the leaderless SMR properties, and the complexity results. The role theorem that explains the trade-off between reliability and scalability, and the chaining effect that can be explored in depth in the extended version of our paper, that explains the reason for the high latency found in real-world implementation of leaderless protocols. So we've run a bunch of experiments with real-world protocols like Ipaxos, and we found a huge latency that can be observed in practice. And this chaining effects, the chaining effect theorem that can be found in the paper, aims at explaining why this happens. So thank you everyone for the attention, and I hope you guys have enjoyed our paper.